Okay, it started now. It should be working. Hello. Hi. So, let's see. What have I been working on? Well, in this demonstration, I'm just gonna show a metacircular evaluator that I've created, and this metacircular evaluator is written in Common Lisp, and it implements a subset of scheme. This is as is found in chapter 4.1 through 4.3 of Structure and Interpretation of Computer Programs. I should start by displaying the code here. I have a repository on the on my GitHub repository. On my GitHub account, I have a repository there. Let me just pull it up. Okay, continuing. Yeah, here it is. This is my account here, and I have this repository. Just opened it up for today, but I've already been thinking about writing some code here for some time, just studying the chapters. So yeah, it's all here. It's all here at that address if you want to go look for it. Regardless, we won't open it up from the web. We can open it up here from the Mac, so perhaps from the terminal. But I'm just gonna show a demonstration of that, and we'll look through some more developed examples later on. Here. Okay, and we'll do. I don't have any implementation for this. Let me explain why I wrote it in Common Lisp instead of Scheme. I don't have a Scheme interpreter. I don't have that. I didn't install that. I was too lazy to. So I wrote it in Common Lisp instead. And I figured I already know more Common Lisp. I know enough to get myself working with something useful, so why not do it here? Yeah, there it is. So it even starts up with its own thing, its own license, and let's try something here. Let me show some of the features. Okay, let's see, what are the demonstrations? Well, numbers. Or actually no, the predicates first. So the predicate T evaluates T nil is nil. We have numbers 486 becomes 486. We have primitives like addition and subtraction. So divide the addition of 3 and the multiplication of 4 and 5. So that's 23. Actually no. Let's go back. No, I can't do that there. The addition of 6 with the multiplication of 4 and 5 by the number 13. That should work. And yeah, that gives us 2, because 26 is the twice of that. And then let's say minus that giant operation 6 multiply 4 and 5 by what is it 1 should give us too few arguments. I think I might have miswritten it. Hold up. Divide plus 6 multiply 4 5 close 1. Too few arguments given to lambda. That might be an error. I haven't really fixed it up entirely yet, but it works. It also has recursive functions. So let's define pi be 3 point. Actually, let's say 3 pi 3. Pi 3. So symbols evaluate to their values. And you can add symbols and multiply symbols. It all works. There's also, of course, another feature that I had to add. Function displaying. The functions themselves work. So let's write the classic example. Factorial of n, conditional, n is equal to 0, return 1, else or otherwise multiply n by factorial of the decrement of n. And that's fact. If we type in fact, it evaluates to the function itself, a closure, but it displays the function body as if it was a lambda expression. I figured that would be well, no, it's not that I figured. I was forced to do that. I was forced to do that because if you just print the actual closure object, the closure has the entire environment stacked on top of it. And when you print the entire environment, that's like listing every atom in the entire world. That overwhelms the underlying Common Lisp implementation, C-Lisp, and it gives me a Stack Overflow, and I can't do anything anymore and lose everything. So that's that. We define the function, but the real work isn't getting the function to work. It's a recursive function, so this is supposed to show that function application works, combinations work, and also recursion works, which means environments also work. Basically, the closures and the environments work. So let's say fact of 5 should be 120. Fact of 4, well, okay, 0, okay, times, okay, factorial of 1. So factorial of 1 is 1, factorial of 2 is 2, factorial of 3 is just 3 multiplied by factorial of 2, which is 6. Factorial of 4 is 6 multiplied by 4, should be 24, and 24 multiplied by 5 is 120, so we get 24, but yeah, we get 24, yeah. So that works. Let's also show lets. Now, I know in SICP at some point it shows that let blocks are just applications of lambda, wherein the function, the variable name, is just a parameter, and the hold up. Let me open this. Open a new window. SICP. I should have opened it before we started. I have to pause again. Okay, back to the recording. Back again. Add it. Yes. The let blocks. Running the evaluator as a program. This is chapter 4.1.4. There's one before it here for the let blocks. Yeah, so here it says in exercise 4.6, let expressions. This is an example of where it is, but it's somewhere here in the text. This is called like transpiling, or what is it? Syntactic sugar, which is simplified. It simplifies the evaluator. There was a paragraph like that. It was like 5 procedure arguments, conditionals, applications, definitions, representing expressions, definitions, and lambda. Make if they did it for cond, and they did it, yeah. Here it is. Derived expressions. There. Some special forms in our language can be defined in this. The cond can become this. Implementing the evaluation of cond in this way simplifies the evaluator because it reduces the number of special forms for which the evaluation process must be explicitly specified. What that means is actually implemented. So which part is actually implemented? And you see the dash arrow, or dash arrow for cond. This is, yeah, derived expressions. Derived expressions, yeah. Derived expressions are syntactic sugar. Let doesn't enter that story. So I guess in the exercise it just says let is a bit equivalent to lambda with these expressions. Let's write something like that. So let's write let fact. Here we're doing this something with a function. Let fact be lambda x returning x, the identity function, and then display fact. Yeah, see, that works. So there's shadowing. We can do an example of object-oriented programming, or message passing more specifically for this. So let's do make object with taking dt for data. Then we're returning a let block. Let data be dt, which returns a lambda, getting a message, and we'll do case analysis on the message. So const eq message get will return dt. Then otherwise eq message, what is it called, set, or actually no, well, eq car message set. So we're either returning get or a list of set and something else, which is stranger. Car, if the car message is set, then the cadder of it is the value. So then we say set dt to be the cadder of message in that case, and also return OK. Let's return the symbol OK. Or actually, no, more descriptively, let's return dt. Otherwise, nil. So we're explicitly failing. That's the object. Make object. This is a constructor. And we have accessors and selectors. So make object. Let's define name to be make object with my actual name, and it's a symbolic data. Okay, name get. Oh no, name get like this. Right? No. With the quote. Yeah. If name get, it gives me my name. Now let's do name set to, I don't know, something else. Jane Doe. Let's set to Jane Doe. Undefined function, no, it failed. Case in point, doesn't always work. It's something about it. Let's start again. So it works. Now let's talk about the code. Let's talk about some other things. I talked about conditionals. Conditionals work. We don't need to talk about all the other things. Let's see, there's function definitions. Have I demonstrated function definitions? Well, I've demonstrated object or message passing to an extent. And I've the actual define fact, not define fact lambda taking n body. No. Okay, we haven't showed begin expression. So let's do begin. Okay, begin define pi 3. Define circle. Okay, let's do circle area taking radius and return multiply radius by multiply